Today we talk about one important theorem which is familiar in functional analysis. We known about that Riesz Representation Theorem. Okay, we first start from this statement of this theorem. Okay, we write this statement. Let X be a smooth Banach space. Let X be a smooth Banach space. And Y be a subspace of X. Y be a subspace of X. And if Y to K be a bounded linear functional, and if Y to K be a bounded linear functional, then F has a unique Hahn-Banach extension of F. Hahn-Banach extension of F. And if x to k and if x to k be a bounded linear functional, then there exists a unique u belongs to x such that if x equal to xu for all x belongs to x. Moreover, norm of f equal to norm of u. Okay. Now we are going to prove of this theorem. So we write proof here. If f equal to 0, then u equal to 0. Is unique element such that if x equal to inner product of xu for all x belongs to x and norm of f equal to 0. Okay. Now we're going to 0 equal to norm of u here. Now we're going to another assumption. Assume that f not equal to 0. Okay. If not equal to 0, then what happen? Okay. If f not equal to 0, set y equal to nf, then y be a closed subspace of x. Be a closed subspace of x with y subset of x. Hence z equal to nf perpendicular not equal to 0. Okay, nf perpendicular not equal to 0. Then what happened? We erase a portion and going to further discussion about that. Now we write here, let z be non-zero element of, let z be non-zero element of this set, and let x belongs to x. Define y equal to fx multiplied by z if z multiplied by x belongs to x. Now note that fy equal to f of x, f of z, difference f of z, f of x equal to 0. Hence y belongs to this capital Y, and now yz equal to 0 equal to fxz difference fzx inner product of z. Okay, then this implies 0 equal to fx z inner product z difference fz x inner product. This implies fx equal to x z xz here if z divided by norm z square. This implies fx equal to what happened x here if z conjugate by norm z square z. Okay, then what happened? Then we write it in this way: fx equal to x u, where u equal inner product of x u, where u equal to if z conjugate by norm z square z. This is not equal to 0. Okay, then we also write in this way. Now we going to prove of uniqueness of u. Okay, we erase our portion and going to uniqueness of u. So we write here uniqueness of u. Then what do? Suppose that p belongs to x such that v belongs to x such that fx equal to xv, inner product of xv for all x belongs to x. Okay, then 0 equal to fx difference of fx equal to x u difference of xv equal to x u difference v. This implies u equal to. Okay, now note note that norm of fx less than equal to norm of v norm of x. Okay, for all x belongs to x, because this is inner product of xv and this must be less than equal to this. Then this implies that norm of a is bounded and norm of f of s is less than equal to norm of b marked as 1. Next we write about Moreover, what we talk about now, we talk about norm of xv. This mod inner product of xv modulus equal to mod of fx less than equal to norm if norm x for all x belongs to x. Then what happened? We take in particular. Okay, this one is a logic. Particular we put for x belongs to x equal to v. We put. Then we have what we get. We get here v inner product norm less than equal to norm if norm v. This one equal to norm v square less than equal to norm if norm v. So this implies what? This implies that norm v less than equal to norm f. This one marked as 2. This one is square. Okay. Then what happened? We erase our portion and going forward. We see about that here from 1 and 2 we get norm of f equal to norm of f. Then what happened? Then the element v is called the representation of f. Vv representation of f. Okay, and obviously we get a unique element u. Unique u. We get one unique u belongs to x such that what? If x equal to inner product of x u where x belongs to x, and obviously with norm of f equal to norm of okay also satisfies this. So we prove this representation theorem. This theorem satisfies, that means gives what? This theorem gives if x be a smooth Banach space and y be a subspace of this x, then we find if y to k be a bounded linear functional, then f has a unique Hahn-Banach extension. This one and obviously if this extension be a bounded linear functional, but here would say about that this functional value of f obviously represented as two elements in our product of this smooth Banach space, and obviously one norm of f equal to norm of this function equal to or norm of any one of inner product element. Okay, that means fx equal to x inner product of some element, this element norm equal to norm of f. We also prove this. Now we're going to forward. We also see one example. Okay, we erase this portion and going to give an example. So the following example shows Riesz representation theorem does not hold for a general inner product space. That means if x be smooth Banach space, then this one holds. But we check it now. We write this example at first. Then what we get from here? Just write x equal to c double 0 and define inner product of xy equal to summation I equal to 1 to infinity xi yi. Okay, for all x equal to x1 x2 xn 0 0 and y equal to y1 y2 yn 0 0 okay. Here write y in or y in, not a problem at all. That means this one is different, then obviously not a problem. Okay. Then after certain terms, this all are contain zero. That means some finite term are or is that means valid and others are zero in C double zeros element. Okay. Then we will define one functional. Take a functional. Functional means what? That means domain must be one field. Okay. Then if C double zero to K defined by domain, sorry, range must be field. Okay. Then this one is functional. Then what? This one x I by I. Okay, where x equal to x1 xn 0 0. Then one can see that if linear, obviously we check about it, but we'll just give this result. We see that if linear. How this one is checked? Obviously you do it. Here you write in this way. I'm not doing it. F x equal to x1, x2, y2, x3, y3, xn, yn, and if y equal to y1, y2, 2, y2, y3, y3, then if x plus fy equal to this one, then this one equal to f of x plus y. Okay. And again f of cx equal to obviously c common, then c of fx, then f be linear. Next we're going to if we interested, then you do it. Something is created some problem here. I think this problem is vanished. Now we're going to also further discussion about that. That means f be linear. Next we also see that f be bounded. How this one? Note that this one is norm of fx equal to I equal to 1 to infinity xi by I, norm of this less than equal to I equal to 1 to infinity 1 by I, this one mod of xi. Okay. Then what happened? Then this less than equal to what? This less than equal to I equal to 1 to infinity 1 by I square whole to the power half, and I equal to 1 to infinity norm of xi square whole to the power half. Okay. So what happened if this one equal to pi square by 6, this one equal to norm of x2. Okay, here pi square by 6 whole to the power half, that means this 1 by n square equal to 1 to infinity equal to pi square by 6. This one is an important result. So what we see that hence it be bounded. Hence it be bounded. Okay. Now we're going to forward. We erase this portion and obviously we erase this portion and obviously going forward. So suppose for contradiction there exists unique element u is not exist. Okay, but we here talk about for for contradiction that there exists unique element u belongs to x such that f x equal to inner product of x u for all x belongs to C double zero, and we can write u equal to u1 u2 un 0 and for x equal to ek for x equal to ek 1 k position. Okay, then obviously f of ek equal to 1 by k, not equal to ek is t. Okay, then this one equal to uk 1 less than equal to k less than equal to n, and 0 if k greater than n. This one a contradiction. Okay, then obviously f of something not represented by inner product of ek and u. Okay, so here we going to one that means one result. We're going to obtain one result. This result is that the following example shows that the following example shows that Riesz representation theorem does not hold. For a general inner product space. For a general inner product space. Okay, so if X be Banach space, then Riesz representation theorem hold. Otherwise, this one is can't be hold. Okay, now we discuss on one important theorem. Also, all are known about that. We also discuss now this theorem. Obviously, this one if X be complex linear space, then this one is discussed. This one is Hahn Banach theorem. Okay, also discussed now. Where is this portion? Because in real linear space, we also discussed that. But now we also discuss in complex linear space. Okay, obviously real also touched. Now we write this statement first. Statement we write in theorem in theorem. We represent it in theorem. Let x be a real or complex linear space. Real or complex linear space, and Px to R and Px to R be a sublinear function. Let Y be a subspace of X. Let Y be a subspace of X. Y be a subspace of X and if y to k be a linear functional, and if y to k be a linear functional, such that such that norm of fx less than equal to px for all x belongs to y, then there exists a linear extension. Then there exists a linear extension if delta of f on x such that norm of f delta x less than equal to x. Okay, now for this one hold for all x belongs to x. Now we're going to further discussion about that. Now we write proof and case 1. When x be real linear space, when x be real linear space, by Hahn-Banach theorem, by Hahn-Banach theorem, obviously there exists if delta x to r such that if delta be linear and if delta x less than equal to ax for all x belongs to x. Now note that f delta x minus f delta x equal to f delta of minus x less than equal to p of minus x equal to minus of px, this one mod, then this equal to px. Okay, for all x belongs to x. Then what happened? Then obviously minus px x, this one obviously less than equal to f delta x. Okay, now then what happened for all x belongs to x? Then what happened? This implies that norm of f delta x less than equal to px for all x belongs to x. Okay, so we here see that norm of f delta x less than equal to px. Okay, and obviously we also that means get one extension and we do this one. Okay, next we discuss case 2. We erase all portion. Case 2 where x be complex linear space. When x be complex linear space, the linear function fy to k can be written as the linear function fy to k can be written as f(x) equal to f1x plus I f2x for all x belongs to y. For f1 and f2 y2 are linear functions. For f1 and f2 y2 are linear functions. f1 f2 y2 are linear functions. Okay, then what happened? Here we write let x belongs to x, then I of fx equal to f of ix equal to f1 ix equal to I f2 ix. Here we write I of fx equal to I of f1x difference f2x equal to f1 of ix I of f2 ix. Okay, then what we obtain thus f1x equal to f2ix and f2x equal to difference of f1ix. Hence fx equal to f1x difference plus I f2x equal to f1x difference I f1 of x. Okay, now what we see here, let x r and y r be subspace of x and let x r and y r be subspaces of x and y with real scalar respectively. Now note that if Jx equal to less than equal to fx equal to square root of f1 x whole square plus f2 x whole square. Okay, norm of this. Then what happened less than equal to px for all x belongs to y. Since f1 y r2 r is a linear functional, here we write j equal to 1 then 2. We erase our portion and going to forward. Since f1 y r2 r be a linear functional by Hahn-Banach theorem, by Hahn-Banach theorem, there exists linear functional f1 delta. There exists linear functional f1 delta x r to r such that f1 delta x norm of this or mod of this less than equal to px for all x belongs to x. Okay. Similarly, there exists a linear functional. There exists a linear functional f2 delta x r to r such that f2 delta x less than equal to px. Okay. Then what happened? For all x belongs to x. Then what happened? Now define here. Define f tilde x equal to f1 tilde x difference I f2 tilde x f2 tilde not f1 I tilde I x. Then f1 tilde be linear functional on x. Okay, define this and also be linear functional. Now we show that this f1 delta x less than equal to px for all x belongs to x. Okay, so how? For x equal to 0 or f1 delta x equal to 0, we have 0 equal to norm of 0 equal to norm of f delta 0 equal to px. Okay, next let f of delta x not equal to 0, then set r equal to f delta x. We can write f delta x equal to r e to the power I theta. Here r equal to e to the power minus I theta f delta x. This one mod of r equal to mod of this. Okay, not here, just write r equal to this. Then what happened? This one equal to f delta e to the power minus I theta x belongs to this r. Okay, this one equal to real part of f delta e to the power minus I theta x equal to f1 e to the power minus I theta x. Okay, so we erase our portion and going to further discussion about that. Hence r equal to mod of f1 delta to the power minus r theta x. This less than equal to p of e to the power minus I theta x. This implies that r less than equal to e to the power minus r theta p of x. Hence, this implies that r equal to mod of f delta x less than equal to p of x. Okay, so We also prove this. We also prove there exists a linear extension f tilde of f such that f tilde x less than equal to px. Okay, so today we stop here.